Section 5-4 is on Riemann sums and the definition of definite integrals. The objective is to use a Riemann sum and limits to define and estimate values of definite integrals. So again, if you recall, the 4 topics of calculus we said we were going to cover: limits, derivatives, definite integrals, and indefinite integrals. So this is that 4th topic there. We were introduced to definite integrals actually back in chapter 1. So you have seen these. Let's just remind ourselves what a definite integral is, first of all. So what we learned back in chapter 1 is a definite integral. One way to define it here for us, just briefly, is that it's a signed area between the curve and the x-axis, between your function and the x-axis. And I say it's the signed area because it can be positive or negative, the definite integral that is. Of course, area is always positive, so it's signed, meaning it could be a positive or a negative result that we get. The other way that we said you could think about a definite integral is it's a product of x and y. When you're finding the product of your horizontal axis and your vertical axis there in your equation, product of x and y is actually a definite integral, versus a derivative is a quotient of y over x, y divided by x. It's change in y over change in x. It's slope. That's a key difference between definite integrals and derivatives for us. All right, so here's the notation that we use to define a definite integral. And the fact that it's an integral should kind of be a hint to us that we're going to use the same or similar notation that you saw for an indefinite integral. They're both integrals. The only change or the difference that you're going to see here is that because it's a definite integral and it's an area, you have to indicate a starting and an ending point that you want to find the area. So I have to indicate that I want to start at A and end at B. And notice we put those as values above and below that integral symbol to indicate the starting and the ending value. So the value that you place below the integral sign is the lower bound, and the value that you put above is the upper bound there. So we're integrating from A to B there. So it's the definite integral of f of x from x equals A to x equals B. And that's the notation we'll use. So you can distinguish between definite and indefinite integrals simply by looking for those values that you put above or below the integral sign. All right, so let's talk about a Riemann sum, which is the topic of this section here. And a Riemann sum is actually an approximation of a definite integral, but we're going to use rectangles. If you go back to what we learned in chapter 1, we were introduced to this idea of definite integrals and finding area below a curve, and we were approximating that area using, first of all, counting squares technique, and then we eventually learned the trapezoid rule, to use trapezoids to approximate it. So now we're going to progress from trapezoids to now rectangles. So that's what Riemann sum is, a rectangular sum of the area below the curve. All right, so let's illustrate what exactly a Riemann sum is here. I'm going to just draw a sketch of some function, and then I'm going to use this to kind of illustrate how we calculate a Riemann sum. I'm going to give myself plenty of room here to draw this sketch in here because there's lots of things that I want to add in here. But let's just say that I have some function here, f of x, and I want to integrate this function or find the definite integral from, let's say that this is A, and we'll say that this over here is B. I want to find the area between the curve and the x-axis, the area below the function and the x-axis. All right. So the first step to calculate a Riemann sum is to subdivide the interval from A to B into n subintervals. So I'm going to kind of flip back and forth between the steps that we're going to go through and their sketch up above here. But the first step is to subdivide this. So I'm going to divide this up into n subintervals here. And I'm not going to obviously sketch all these. I'll just put, I can put one more here. I'm just going to dot, dot, dot to indicate that obviously continues there. And we'll say that that is our last rectangle that we'd have, or last subinterval that we'd have there, which will eventually be a rectangle. All right, so we've got it subdivided into n subintervals. The next thing that we need to do is to calculate the width of each subinterval. And actually the way that you calculate the width of each subinterval, if you recall from trapezoid rule, it's the same calculation. To calculate the width of of each subinterval, you take the width of the entire interval from A to B, which would be B minus A, and you divide that by the number of subintervals that you split it up into, divided by n. So B minus A divided by n will tell you delta x. It will tell you the width of each subinterval. So if I come back up here to my sketch, we'll just mark those up here on my sketch, that this width right here is delta x. And this width right here is also delta x. And this is delta x. And so forth. Now, the width of each subinterval, by the way, does not have to be the same. It makes the problem a lot easier if they are the same. Same is true with trapezoids. You don't have to have the same width for each subinterval. The only thing that's nice about having the same width is it makes the formula a little bit easier to work with there because they're all the same width. But I could still calculate the area of this thing. I just have to calculate the area of each individual rectangle and add them all up. I'm going to see that there's a nice formula that I'm able to use to combine all that here in a second. Similar to what we saw with trapezoids. With trapezoids, we wrote down the area of each trapezoid and then added them up. And I saw there was a nice way to rewrite that formula once we kind of combined all those things. And that happens as long as the width of each subinterval is the same. All right, so we've calculated delta x, and I've actually indicated what the measurement of delta x is there on our sketch. All right, the next thing that we have to do is, it's a kind of an extra step we have to do here that we did not have to worry about with trapezoid rule. And we have to pick what's called a sample point. We're trying to sketch a rectangle. And in order for me to sketch a rectangle, I need to know how tall it is. And so that's what these sample points are going to be. Pick sample points C1, C2, C3, and so forth, all the way up to C sub n in each subinterval. And we're going to end up using these sample points to determine the height of each rectangle. We'll see that in the next step there, but that's what these are leading to. It's helping me figure out what the height of each trapezoid is going to be. So I'm going to just go ahead and pick some sample points, and it can be anywhere in each subinterval. So I'm just going to say for this first subinterval, well, let's say that C1 is going to be over here. And let's say for the second subinterval, maybe I'll make C2 right here. Maybe for the third subinterval, I'm going to actually make it over here on the far right side of that subinterval. So we'll call this C3. It can be anywhere in the subinterval, including the endpoints there. And then let's say that this is maybe C4 right here. Okay. Sometimes there will be some uniformity as to how we pick those sample points. Other times there might not be, like I'm doing here. Just depends on the problem that you're given. And then let's indicate for the last subinterval, let's just say that C sub n would be right here. Okay. So we've picked our sample points. Pick a sample point in every single subinterval that you have. All right, now the reason for those subintervals, like I mentioned, we have to determine the height of our rectangles. And that's what the sample points are going to help us do. We're going to let f at c sub 1. So plug in c sub 1 into my function. That gives me a y value. In essence, it gives me the height of my rectangle. F of c2, f of c3, all the way up to f at c sub n be the height of each rectangle. Okay, so let's go back up to our sketch and actually illustrate that here. So I'm going to take c sub 1, and I'm going to draw a dotted line here to go up to my curve. So right there is the value f at c sub 1, and that right there is going to be used to determine the height of this first rectangle. Let me go ahead and finish marking these points, and then we'll sketch in our rectangles here in just a second. Here's f at c sub 2. Here's f at c sub 3. Here is f at c sub 4. And so forth all the way to f at c sub n is going to be right here. Okay? And so to sketch in our rectangles now, we're going to sketch our rectangle with, of course, the base that is indicated with delta x, but then the height is going to be represented by this point we just plotted. So that first rectangle looks something like this. All right, if you want to draw in the base there, I guess we can mark that as well. And the second rectangle will have a height that's about right here based on the point that we've plotted. And so the second rectangle looks like this one right here. And the third rectangle looks like this. And the fourth rectangle, just a slight bit taller there than the last one. It looks something like this. And so forth. You keep doing this all the way up to the very last rectangle, which has a height about right here. And there's the last rectangle. Okay. You can see how some of these rectangles are above the curve a little bit. Some of them are completely above. Some of them might be completely below the curve. Some might have a nice little mix there where it's partly above, partly below. Just depends on where you pick that sample point as to what's going to happen there, of course. All right, so we've got our rectangles all sketched, all n of our rectangles. And now the question is, can we find the area of each rectangle? Well, I know the area of a rectangle is base times height. And the base of each rectangle I know is the delta x. So the delta x is representing my base here. And the height is the points that I just plotted. And those were the f at c sub 1, c sub 2, and so forth. So we'll call those f at c sub k values, where k, of course, goes from 1 to n. So the area of each rectangle can be calculated by taking f at c sub k and multiplying it by delta x. And then finally, we want to calculate the Riemann sum. Now the Riemann sum is the result that you get by adding up all of these rectangles. So let's see if we can actually add all those up. We'll do that down below here. So to calculate my Riemann sum, first of all, the Riemann sum, just like with the trapezoidal sum, we called it T sub n. For a Riemann sum, we call it R sub n. It stands for a Riemann sum. R also stands for rectangle here, just happens to be the same letter, of course, but it actually is a Riemann sum, is why we call it R, but you can remember it either way. And so the Riemann sum here, to calculate it, I need to take the area of all of these rectangles and add them up. I'm going to write it, first of all, in a summation notation using sigma. And the way we'd write that is it's the sum from k equals 1 to n of the area of each one of these rectangles. So it's f at c sub k times delta x. There is our formula that we're basically going to write down. That's the concise way to write that. But let's actually kind of write this out and just see what we end up with, of course. If we were to write this out term by term, the Riemann sum would be my function at c sub 1, that's the height, times delta x. And then I add that to my function at c sub 2 times delta x. And I add that to my function at c sub 3 times delta x. And so forth, all the way up to my function at c sub n times delta x. Again, if I go back up here to my sketch, you can see that all I'm doing is I'm taking the function height there at c sub 1, that's the vertical distance there. That's the height of the rectangle, times the base of the rectangle, which the base of all these rectangles has a width of delta x. So by simply multiplying delta x times my function values there, and adding all those up, I get my Riemann sum. Now you'll notice, just like we had with trapezoidal sum, turns out that each of these are multiplied by delta x. So because of that fact, I can factor out a delta x actually, and I can rewrite this as f at c sub 1 plus f at c sub 2 plus f at c sub 3, and so forth, all the way up to your function at c sub n. So it turns out to be delta x times the sum of n y values, n function values here. Turns out to be a nice way to remember that. It's very similar then to trapezoidal sum, but remember there is a difference here. We'll see that in our first example, but just realize it's very similar, but know the differences between the two. All right, that is our Riemann sum. Now, there are actually 5 special Riemann sums that we consider because of the fact that you can pick the sample point. Unlike a trapezoidal sum, once you're going to calculate the area of the area under the curve there using a trapezoidal sum, you're pretty much set as far as what the base and height of your trapezoids are, because they're determined by the endpoints of each subinterval. But because of the fact with a Riemann sum that I get to pick these sample points, there's different places I can pick sample points, and thus I get different Riemann sums. So let's take a look at this first one here, which is a midpoint Riemann sum. And because it's a midpoint Riemann sum, we call it M sub n. All right. So I'm going to just sketch a curve here. This will be f of x. And let's say that we want to find the area from A to B. And I'll just split this up into n subintervals here again. And so a midpoint Riemann sum, as its name kind of indicates here, what we're going to do is we're going to find the area under the curve by using rectangles, of course. But we're going to pick the sample points or the height of each rectangle by picking the midpoint of each subinterval. So on this first subinterval, we'll say the midpoint's about right here. We'll call that C sub 1. On the next subinterval, it looks like the midpoint's about right here. So we'll call that C sub 2, which gives me that point. And then the next one is C sub 3. Looks like it gives me that point, and so forth, all the way up to the very last subinterval. We'll call this C sub n. And we end up with that point up there. And so if you sketch in your rectangles, you can see that you end up with the definite integral represented by the sum of these rectangles right here. Okay, and that right there is our midpoint Riemann sum. And it turns out that, of course, since it's a midpoint Riemann sum and we're still using these sample points, the formula is still the same. It's just that we use m sub n to indicate that it's a midpoint Riemann sum. And that's the one that we're going to use here first in this section. There's 4 more we'll talk about in the second half of this section. All right, so take a look at example 1. Example 1 there asks us to find the integral, the definite integral from 1 to 4 of 1 over x dx. All right, and it says to do a little bit more than what we're going to do. So we're going to just find m sub 6. That's the midpoint Riemann sum using 6 subintervals. And we're also going to do a trapezoidal sum. And then we want to determine whether these are overestimates or underestimates. So we'll have to look at our results and see what we end up with as to whether or not this is an overestimate or an underestimate. So let's write down our problem here. They said to find the definite integral from 1 to 4 of 1 over x dx. Again, the fact that we have those numbers on that integral sign, 1 and 4, tells me it's a definite integral, not an indefinite integral. All right, and I want to find, approximate this, I should say, using a midpoint Riemann sum. Now I'm going to start out with a sketch of this, and just to help us see what's happening here. And sometimes a sketch might help when you're first doing these, but you'll eventually get to a point probably that you don't need to sketch these every time. If you want to use your calculator to graph 1 over x is a hyperbola. It looks kind of like this. And let's say that this here is 1, and this will be 2. Oh wait, actually I need to go all the way up to 4 here. So 1, 2, 3, and 4. And it says that we're going to do a midpoint Riemann sum here with 6 subintervals is what we want to have here. So we got to split each one of these in half here. I've got a total of 3 subintervals from 1 to 4 already. I'm going to end up having to split those in half. So I'm going to get something like this. Okay. And since they want us to find m sub 6, that's using a midpoint Riemann sum. So that means in this first subinterval, the first subinterval, if I go ahead and mark these endpoints here, this is 1, and then 1.5 would be right here. And then 2.5, of course, is the next. 3.5 is the next one that's not numbered there. And so the midpoint of this first subinterval is going to be right here. That midpoint there is, of course, halfway between 1 and 1.5, so that's at 1.25. And the first rectangle then that you end up with is this guy right here. All right, we'll sketch one more here. The next one here is the midpoint between 1.5 and 2, so that would be at 1.75. And that would correspond to a height right here. So you'd end up with this rectangle like this, and so forth. You can sketch in the rest of your rectangles if you want to see all of them. All right, so our midpoint Riemann sum, m sub 6. Remember that you always need to write down for me the formula that you're using to calculate this. So m sub 6 is equal to, it's the change in x, delta x, remember. In fact, I'll go ahead and put that up above here. Delta x, remember, is b minus a, so that's 4 minus 1, divided by the number of subintervals, which is 6. So that's 3 over 6, that's 1/2. And you can also see that in our sketch. We said that first interval, subinterval goes from 1 to 1.5, so that's a width of 1/2. So it's 1/2 as our delta x, and then you multiply it by the sum of these 6 function values. So it's going to be your function starting at the first midpoint, which is at 1.25, which once you know the first midpoint, if I add on delta x, 1/2 plus 1.25 gives me 1.75 as the next midpoint. And you can see that in our sketch up above there. Add on delta x to that, you get f at 2.25, and so forth. Again, list the first 3 is sufficient, and then the last one, if you want to look at your, maybe I should have marked that up here on my sketch. My last subinterval here goes from 3.5 to 4, so the midpoint there is 3.75, giving me this rectangle right here. And so it's my function at 3.75 is the last one. Write down your calculation. There's your calculation. That's the work right there. And now let our calculator help us calculate this. So you could punch this in right on your home screen there, and you could actually do that calculation. But just like you have a program to do a trapezoidal sum, we also have a program that will help us do Riemann sums here. And I'm going to give that to you here to use. So let's try using that here. Let me bring up my calculator. And actually, let me first calculate this from the home screen, and then I'll show you how you can use that program. So our function I'm going to put into y1, which is 1 over x. And I'm just going to calculate this right from the home screen there, just like we had up there on the board using function notation. So it was 1/2, and then you take your function, which is in y1, and evaluate it at 1.25 plus y1 at 1.75 plus y1 at 2.25, and add on y1 at 2.75, y1 at 3.25, and the very last one here, y1 at 3.75, and just make sure you got that typed in there correctly. So it's the delta x times the sum of those 6 y values there. And that looks like we got it typed in correctly there, and let's let it crunch that value there for us, and it looks like it gets a value of 1.377, I guess, if we round that to three decimal places, 1.377. Okay. Now if you run the program here is called Riemann. You have to have y1 has to contain your function, which is 1 over x for us. And it's going to go through a similar set of menus here for us. The equation is typed into y1. We're going to start out at 1 and go to 4. Put in the actual starting and ending values, not what the midpoints are that we were using. The actual starting and ending values. We want to use 6 increments or 6 rectangles, however you want to describe that. And we're calculating a midpoint Riemann sum, so use option 2 here for midpoint. And when we run that, it gives us again the little formula that shows us what we're actually calculating. But here's the result. Notice we get the same result there. Okay, and it looks very similar to what we saw with our trapezoid program. In fact, that's what our next task is here. They asked us to also do this using our trapezoid program, or using a trapezoidal sum, but we're going to use the program, of course, to help us out. So T sub 6, your trapezoidal sum. You got to go back perhaps and remember what this is, but it's delta x times 1/2 your function value at the first x value. So if you go back to your sketch here, we're starting out at x equals 1, so it's our function at 1. And then it's plus your function at the next point, which is at 1.5, plus your function at 2, and so forth, all the way up to 1/2 your function at the very last value. So the nice thing about this is that it's a little bit easier to see those values because you don't have to worry about midpoints here, but still got to get all of them listed. There's actually 7 y values that you're summing up, but you're only taking half of the first one and half of the last one. So in essence, those two combine to give you just 1 y value, kind of. So let's let our calculator crunch that for us. Again, you could do this right from the home screen, but I'm going to use our trapezoid program. And so we'll run trapezoid. We've got an equation in y1 still. We're going to go from 1 to 4. And we want to break that into 6 subintervals. Again, it shows you the formulas that you use to calculate delta x in your trapezoidal sum. And let's see the results here. The results, T sub n is equal to 1.405. 1.405. So those are relatively close. There's a slight difference between the two of them, but they're relatively close, like we would expect. All right. Now the second part of this question was to determine whether these are overestimates or underestimates. So that's the next piece that we need to figure out. Are these overestimates or underestimates? And if we look at a sketch here, it will help us see what the result is giving us. Let's start with the trapezoidal sum. And you have to consider the sketch of your function here in order for you to determine what's happening with the trapezoidal sum as far as whether it's an overestimate or underestimate. We've done this before, but you've got a curve. Let me just sketch a curve here that looks like our function. It looks something like that. And I'm going to draw one big trapezoid in here just to kind of exaggerate it a little bit, but it'll help us see that. It's in fact an overestimate that when I draw on the top of my trapezoids, because my function is concave up, it turns out that I'm including this little chunk of area here for every single trapezoid. Obviously, the more trapezoids I use, it reduces that error, but it's definitely an overestimate. So that tells me that I know that my answer that I came up with for trapezoids, 1.405, the answer is actually less than that number. Okay. Now you can do something similar here with rectangles, your Riemann sum. Again, I'll just sketch a function here, and we've got a decreasing concave up function, and I'm going to sketch in, again, kind of one subinterval, but I'm going to exaggerate it a little bit so it's a little bit easier for us to see what's going on here. And then I got to pick the midpoint here as the point that I use for the height of my rectangle. So I end up with a rectangle like this. So you can see over on the left there, I'm not including this little piece of area that I should be. This little chunk over here, I'm not including, and I should be. Versus over on the right, I've got this little chunk right here that I am including that I shouldn't be. It's above the curve. But they kind of almost look like they're going to balance out. They're not quite the same area, but they're close, it looks like. Now you can look at these two areas and kind of look at the slope of your curve to help you figure out which one of these is going to give you more area, at least approximately. If I were to consider that these are two triangles here, I know they're not quite triangles because it's got a curve that it's going through, but if I were to sketch in this little triangle right here, and if I were to sketch in this little triangle over here, again, it's not quite a triangle, I realize, but it's approximately a triangle, or pretty close to it, that because of the fact that I've picked the midpoint of each subinterval, that means that this is actually 1/2 of delta x as the base for both of these triangles here. So they have the same base, but their heights are going to differ here based on the slope of this curve here. I can see that over on the left, this curve has a much steeper slope. So the height, I'm going to call this just h1 here for the height on the left side there. The height on the left side, because of the fact that it's a steeper curve on the left side, is going to be much greater. It drops much faster through this width of 1/2 of delta x versus this height over on the right side that we have, h2. So it turns out that h1 looks like is greater than h2. And because of that fact, and I know the area, of course, is 1/2 base times height. They have the same base, and their heights is all that differs. So that means that the area over on the left side is greater than the area over on the right side. So in other words, we're leaving out this green section, which is more area, than we are including over on the right side. So in other words, we're leaving out too much area. This is an underestimate, is what we see on this one. Okay, and it comes down to the fact that the heights of those two little triangular shapes there are different. And once I can figure out which one has a higher or has a greater height based on the slope, I can determine which one of those is going to give me the greater area. All right. That was the example they want us to look at. One last thing that I want to talk about here is the connection here between trapezoids and rectangles. That you've seen the trapezoidal sum, of course, already. You've seen a rectangle using Riemann sums. And the question is, which one of these is more accurate? That's a natural question that you might have. Or you might even look at that and say, well, it looks like the trapezoids is a much better approximation. And let's take a look at those two a little bit closer here. So let's start out with trapezoids. And I'm going to sketch a curve here. And I'm just going to sketch a curve like this. And I know that when I go to calculate the area of this using trapezoids, that I'm going to end up working with this trapezoid that uses these 2 points right here as the points to determine the 2 bases of my trapezoid. And so you can see in this case that because my curve is concave down this time, that I'm always going to be leaving out some little chunk of area here. I'm always going to have this error that's involved with trapezoids. The only way I'm going to get the exact area, in fact, using trapezoids is if I got a straight line. If it's a linear function or a horizontal line, I'll get the exact area using trapezoids. But any other curve to it, I'll either be underestimating or overestimating because of the fact that my trapezoid is either below or above the curve. All right? Versus if I were to take that same curve here, or a similar at least looking curve, we'll call this f of x. I should call this one f of x over here as well. And let's just split this up into some interval here from a to b again. In fact, I should have named that over here. We'll call that a and b. If you remember that our technique for rectangles, the extra step involved with rectangles is the fact that I have to determine the height of my rectangle. So I have a little bit of freedom here of picking the height, unlike working with trapezoids. Once you set your subinterval, your trapezoid is set. Here, once I set my subinterval, that's the first step of setting what the base is going to be, but I still have to determine the height of the rectangle. And so the question is it possible that I could get a better and better approximation of this area using rectangles of differing heights? And I would suggest to you, I'm going to kind of approximate it here, but I would suggest to you that somewhere about right here, if I were to construct this rectangle, that this area right here that I'm leaving off versus this area over on the left that I'm including are roughly the same size. In fact, if you think of this as being kind of sand here, that I could kind of shift around this curve that I start out with, and I could take this sand and push it over into this section, and then smooth it out, you could see that I would end up with a rectangular shape. In other words, there is a rectangle. In this case, there's exactly one rectangle that if I could find this sample point right here, we'll call that C. If I could find that one sample point, it turns out that the area of my rectangle is exactly, not approximately, not close to, not relatively similar, but exactly the area under the curve. That's the goal. In fact, that's the next step that we're going to take, is how do I carefully come up with these sample points in order to get the areas of my rectangles to be exactly the same. This is the advantage of using a rectangle as opposed to a trapezoid. All right, and that's the end of our discussion for right now.